All right, so I think I've cracked it. I think I've got it. I talked to Kopacki. He says that my slides look good, and I'm understanding it. So I think I've got it. All right. So the indirect pathway in a healthy patient, and thinking about undesired movement. So we have undesired movement that needs suppression. You've got glutamate that is released through the motor cortex, and it goes to the striatum, and it is excitatory on the striatum. Then also from the substantia nigra, you have dopamine, which is binding at D2 on the striatum. And dopamine actually is inhibitory on the striatum. It's actually the balance between the glutamate and the dopamine binding at D2 that decides whether or not the striatum is activated or not. But in an undesired movement in a healthy patient, the glutamate is going to kind of win. And so the striatum is going to be activated. It will release GABA, which is inhibitory on the GPE. Because it's inhibited, the GPE is not going to inhibit the subthalamic nucleus. So that will be activated, release glutamate, which will stimulate the GPI, which will release GABA, which will inhibit the thalamus. So you won't have stimulation of the motor cortex, and the undesired movement will be suppressed. That's in a healthy patient. But before we move to a Parkinson's patient, what about if there's a movement that's desired? We've talked about this idea, maybe more specifically of the thalamus, but like a brake versus a gas pedal. The direct pathway is all about, initiating a movement that you want. Whereas we think mostly of the indirect pathway is like saying, stop, don't do the movement, don't do the movement. But if it's a movement that you actually do desire to do, you don't want the indirect pathway to say, no, don't do it. So there's a mechanism for that. And that's where the dopamine comes in. So when the movement is desired, dopamine is released to reward that movement. And so dopamine wins in this case and inhibits the striatum. So the GPE is not inhibited. And then because it's active at baseline, it will inhibit the subthalamic nucleus, and it goes through. And ultimately, your motor cortex will receive stimulation from the thalamus because the thalamus is not being inhibited. And then your desired movement, it happens. It doesn't get stopped by the indirect pathway. So I think our real point of confusion in class is all about this regulation of the striatum. The idea that yes, glutamate is excitatory and dopamine at D2 is inhibitory, and they are in balance. And in undesired movement, the glutamate wins. What about the Parkinson's patient? A little bit more complicated. So again, we have an undesired movement that needs suppression, but this time we're in a Parkinson's patient. So you do, I presume, get your glutamate released, and it's binding the striatum, and it is exciting it. However, we know that you do not have as much dopamine coming from the substantia nigra in the Parkinson's patient, and so you have a lack of dopamine binding at D2. And this is going to lead to a hyperstimulation of the striatum, and that actually is going to mean that the GPE is over-inhibited. It's too much inhibition, and then like before, it's not going to inhibit the subthalamic nucleus, and it's going to cascade through the entire indirect pathway, leading to an overactivation of the indirect pathway, too much indirect pathway. So the GPI is overexcited, the thalamus is over-inhibited. You've got too much inhibition of the thalamus, which also kind of hung us up a little bit because it seems counterintuitive. We talk about the indirect pathway as being the responsible for tremor in the Parkinson's patient, whereas we talk about the direct pathway being, more responsible for the bradykinesia and rigidity. So what's going on here? Well, because the thalamus is over-inhibited, you're not going to get normal signaling, but you actually don't get no signaling at all. Counterintuitively, you end up getting these bursts of stimulation, and this happens because of multiple mechanisms, one of which is this idea of hyperpolarization of the neurons in the thalamus. Because they get so much inhibition from the GPI, they end up becoming hyperpolarized and open up some ion channels that lead to this rebound burst firing. So that's what these purple arrows are showing, is a dysregulation of the communication between the thalamus and the motor cortex. So the thalamus leads to these bursts of firing that are dysregulated, and that's what causes, ultimately, your tremor. You do maybe get some bradykinesia and rigidity from the indirect pathway, which makes sense because the thalamus is inhibited, you'd expect less movement. But you do get the tremor as well, and that's because it's getting so much inhibition, the stimulation is actually dysregulated and disordered, and that means that you are getting these bursts of stimulation that lead to tremor. So that's what I have for the indirect pathway. I also made some slides for the direct pathway, and I think we were a lot more straightforward on that. But for the direct pathway, just for completeness, you have desired movement. This is a healthy patient. Desired movement, glutamate, but in the direct pathway, dopamine from the substantia nigra binds at D1, which is actually excitatory for the striatum. And in this case, the striatum is going to do complete inhibition at the GPI, which means that the thalamus is not inhibited, which means it triggers the motor cortex, which then tells the muscles to move. This is how we're doing our movements. You get all this signaling here that basically tells the body, yes, move. But in the Parkinson's patient, you have a lack of dopamine at D1. And so even though you're still receiving glutamate, you have less excitement at the striatum. And dopamine does play some specific roles. We talked about like fine tuning or initiating and selecting movements. And this leads to still some inhibition of the GPI because you do still have activation from glutamate, but it's only partial now. That's what the dotted lines are showing, that you're not getting full inhibition. And because the GPI is tonically active at baseline, at least talking about the direct pathway, you're going to get some inhibition of the thalamus. And so you're going to have some reduced signal to the motor cortex. And this reduced signaling from the thalamus to the motor cortex is going to lead to your rigidity, bradykinesia, decreased coordination, some of the things that make sense, like having a harder time starting those movements. They're going to be maybe less fluid. Think about your cogwheeling. And that's ultimately because you have less stimulation ultimately reaching the motor cortex. I think it's worth noting, you can read this down here, just the idea that both the direct and indirect pathways are happening at the same time. And so they're going to kind of converge on the GPI in the Parkinson's patient, and they're going to kind of add on to each other. So you'll see how it really messes with how the thalamus is signaling to the motor cortex in the Parkinson's patient. I hope this was helpful. I did go through at least the indirect pathway with Kopecky, so I think it's all good. I think there were just a couple points we were confused on. I hope this is helpful to people.